Good morning, good morning. Welcome back. We are on page 34 today. So just a couple of announcements before we jump into page 34. First of all, I've just handed out our very first and last take-home quiz. It's the memorize all of these derivatives and antiderivative formulas. So the fact that it's a take-home quiz means I am trusting you to just take this at some point on your own without having the answer key, which you also have right next to you. So when is this take-home quiz due? Let's go ahead and say this thing is due on our review day, which at the moment is February 22, which is that a week from Friday? Is that right? Yeah. So 1 week from this Friday, at some point in the next week and a half, memorize not the whole page because you already have most of it memorized, I hope, but memorize the ones you don't yet know. If you weren't here on Monday, I know there was some bad weather, I have handouts for you. So just raise your hand if you weren't here Monday. What's that? Oh, good. All right. So again, you have the answer key. It was on the back of the updated schedule that I gave you on Monday. Those are the answers. You now have a blank take-home quiz. You have 2 copies of it. If you wish, you might just take it once at some point without trying to study, just to see how many of them you don't know. You might not need to go through and memorize all that many. And then you're going to score it yourself. And if you're not happy with your score, um, I have more copies of the thing, and you can take it a 3rd or 4th time. Like honestly, I want people to get 38 out of 38. That's the goal, is to know those 38 facts, know them cold. Okay, so take it as many times as you need, and then eventually hand it back to me where it's perfect. Any questions on that? Okay, so again, that'll be due February 22nd on our review day. All right, so that is that. Also, I think that on Monday, somebody maybe left their packet here. Is there anybody who doesn't have their packet? Let me know if that's yours. Monday. Yeah, I think it came in on Monday, but yeah, that's you. Okay, good. All right, so here's our calendar. We are on day number 2 of substitution. A couple of things of note. First of all, project 2 is now officially due, so hopefully I had some turned in the other day, but hopefully I've got the rest of them turned in right now. If you haven't finished project number 2 yet, I'll take it within a week, but there are varying penalties associated with turning it in late, but hopefully it's in the folders now. I'd always encourage people to check their answers with their neighbors. These projects can be quite challenging, and you want to make sure you're really answering the question, answering all of the questions. It's easy to miss some things, so certainly check in with each other. Project number 3 is now officially assigned. I handed it out on Monday to most of you, so that thing will be due on February 22, which is a week from Friday. Okay? Sure. Thank you. There you go. Okay, and then the other thing of note coming up this Friday is our second quiz. It's on classes 5, 6, 7, and 8, which we can highlight here. So our second quiz is going to be on those topics right there. That's coming up on Friday. And as usual, you can start the quiz 10 minutes early, so show up for an 8:30 start if you're able and you want a little extra time to take that quiz on Friday. Any questions on any of that? Okay, then if we're all set, we'll go ahead and start on page, I think it was 34. And one thing I wanted to show folks before we start was a nice little shortcut that Ashley, who's not here at the moment, she wrote it on one of her homeworks. She didn't intend it to be shared. I hope it's okay that I'm sharing it, but I think it was really great. This is supposed to help us find the derivatives of sine and cosine and the antiderivatives. And the reason it's difficult is because they just flop back and forth. Sine becomes cosine and cosine becomes sine, but sometimes it's negative and sometimes it's positive. So here's what Ashley had written on her page. She starts with sine and cosine and then the same thing but negatives. That's easy enough to just memorize and put this right at the top of your test when you take it or your quiz. And here's the trick, is that if you want to find derivatives and you go down this list. So the derivative of sine is cosine. Derivative of cosine, negative sine. Derivative of negative sine, negative cosine. Derivative of negative cosine, it just goes right back around to the top, or put another sign at the bottom of this list if you want to. Okay? So if derivatives go down the ladder, then what else can we say? Integrals go up the ladder. So if you want to find an integral, you go up this string. So what's the integral of cosine? It's sine. And the integral of sine? Negative cosine. That's nice, isn't it? Yeah. So thank you to Ashley. All right. Let's go to number 1, and we'll start with Chris. Okay, thank you. Number 2, Ernie. Okay, so let's give this one a shot. So the only thing that's new for this problem is that it's a definite integral. We have numbers, we have limits on that integral sign. So let's go ahead and do the same process that we did before. This is going to be a U substitution. And I know it's very early on in your mastery of U substitutions, but I'm hoping that we're starting to get a flavor for why U substitution might work on this one. Any suggestions for what we could let U equal? For +1, if you see something inside of parentheses, that's always a candidate for what you can let U equal. And then before we do the rest of the process, there's a real good reason that we should see right off the bat that this has potential. What's the derivative of this thing? Is 2x, and I don't worry about the 2, it's x, as Dave says. And I see an x sitting right there in the front. This is going to work. Right? That x right there is matching up almost perfectly with the derivative. So you can maybe save yourself a little bit of time by thinking, a step or two down the road to see if the U substitution you're trying has any potential. This one has a lot of potential. Okay, so our original integral equals integral 0 to 2. Let's see, so then we get the U in here, bare bones minimum. How do I get the U in here? What else do I need to bring in? Is the cubed, right? The U is physically inside of the cubed function. And then I'm going to underline in green whatever is in the original that isn't down here yet. What am I underlining? X and dx, right? And then we need to find x dx in the last purple equation, the derivative equation. So what do we do to both sides? Divide by 2. And so that means that right down here, instead of x dx, I put what it's equal to, du over 2.
Maybe jumping ahead a bit, but if this was like a related rates type problem, instead of writing dx, we could actually write how it related.
Instead of writing dx,
or du, probably like we replaced it with the actual rate.
Oh, we substituted a number. Yeah, so all our related rates questions had a d something dt. For time was almost always the underlying thing. And then we replaced with a number. But we're not going to replace the du with a number at any point in this, or the dx. It's yeah, I see the connection you're making here, but the things that are going to get replaced with the numbers are the x's. That's what 0 and 2 represented in the beginning. Yeah. Okay, so let's continue with our integral here. What can we pull outside to make the integral look nicer? So 1/2. Integral 0 to 2 u cubed du 1/2. It is very tempting to substitute back, to replace the u with the x's right now. It's too early to do that. You have to do your antiderivative. The point of changing from x to u is that the x's were in a complicated integral that's not on our list. You get to the u's, and hopefully you make an integral that is in the list. U cubed du is one of the 8 things in our list. What's the integral of u cubed du? U to the 4th over 4. add 1 to the power, divide by the new power. Do we need to put on our plus C stamp? No, this is our definite integral. We don't need to do it. We do need to put the 0 and the 2 over here. Remember, we had either brackets. If you want to write the whole things, you can put brackets and then 0 to 2. Or you can get away with just putting that vertical line if it's one term. Now that's a little bit misleading right there, because it looks like we're about to put in the 2 for what? For the u. Is that what the 2 represented in the beginning? No, the 2 represented an x. So if you just plug the 2 in for u, you're going to get the wrong numbers right now. And I just want to point out, this is the incorrect method that we're doing here, because it looks like what we've written says plug 2 in for u. So how can we get the right answer? Well, right now we can substitute back in. I'm going to point out that this is x equals 2 and x equals 0. So let's just go back to our x's. Instead of u to the 4th, x squared plus 1 to the 4th. And that's divided by 4. Dave? You can. And that will probably make things easier for us. All right, so now that we've substituted back, now it's legitimate to plug in the 0 and the 2 for the x's. David has a good idea. Let's take that 4 out to the front and make one constant in the front. What does it become? It's 1/8. And then we'll just go ahead and plug in the 2 and the 0. So we plug the 2 in, 2 squared plus 1 to the 4th minus, plug the 0 in. We're just going to get 0 when we plug 0 in, right? We can ignore it. Yeah, be really careful. A lot of times when you plug 0 in, you get 0, but occasionally you don't. So just be really careful when you plug that in. So I think that's 624 in the big parentheses. Is that right? Yeah. Okay, and this guy reduces. Does that go in? 78. Thank you. Any questions on that one? Cassidy. That's a good question. What do we call that vertical line? I don't know. Can you look it up? It must have a name, but I don't know what it's called. Yeah, same symbol with a different meaning. That's right. Okay, so this is the wrong way to do it, because if I just saw this and the two numbers there, I'd say, oh, they mean to plug in 2 and 0 for u, because that's the variable that's there. And that's why it's wrong. So let's do it the right way. So the right way looks an awful lot like the wrong way. So I'm actually just going to jump basically to almost the end of this process. We were trying to integrate u cubed du, and then there was an over 2, right? This is what we had? Yes, somebody confirm. We had that written at some point? Okay, so what made it wrong was that we had a 0 and a 2 on the integral sign, but now the variable is u. Well, you can't have the x's, the 0 and the 2, when we're changing it to u. So this is the only difference. When x is 0, how much is u? When x is 2, how much is u? That's all we need to do. Yeah. The very first thing we said was u is equal to x squared plus 1. So we just plug those two numbers in to the x squared plus 1. So when x is 0, how much is u? Is 1. And when x is 2, 5. So here we have 1 and 5. Okay, can you guys finish this one? Hopefully we get the same 78 that we got before. At no point do you need to go back to the x's for this. As soon as you do your antiderivative, you get to plug 1 and 5 in for the u. Okay, any questions on doing it the right way? We get to the same answer, but somewhere in the middle of this process, we wrote things that weren't true. So that's all. This integral is not equivalent to the original because this says, without knowing anything else, this says you're plugging u in for 2 and 0 for the u. That would look very strange. Yeah, do it the right way. It's not any more or any less work. It's equivalent in terms of how much work it is. So let's just write it the correct way. So the moment you change from x's to u's, just change the numbers. It's real easy. All right, so let's skip. There's some challenge stuff. We're going to skip 4. Just want to make sure we have enough time for the group thing. Let's go to 5. So let's try this integral of tangent of x dx. I think I mentioned in class that on this take-home quiz that you guys are going to do, there's actually one formula that you don't know yet. Did I mention that the other day? No. I did or I did? I did. So anybody find the formula that's on this sheet that I said memorize that we actually have never seen before? I'll give you a hint. It's on the whiteboard right now. So the integral of tangent of x, it's on the sheet, but we've never seen it. Yeah, that's what we're going to do. I mean, again, integral of, so tangent. Did tangent come from the derivative of any function that we've seen? The answer is no. We can take a derivative of tangent and we get secant squared. Some of you need to review your tangent derivative. So we can go that direction, but that doesn't help us find an antiderivative of tangent. So the technique here, it's kind of clever, is you rewrite it as a sine over cosine. That seems worse. It seems more complicated. But if you're trying to find an antiderivative with a fraction, a u substitution that you might always try is letting u equal what? Top or the bottom? The denominator. Hoping it turns into a 1 over u, because we can handle 1 over u. It came from ln. So let's let u equal the bottom. So the derivative of cosine, we have Ashley's trick if you're still not sure whether it's positive or negative. What is this one? It's negative sine. So this integral becomes bare minimum. Where's the u? Yeah, so it's a 1 over u. I'm just going to put the u down there to get a bare minimum. We put the u in. And then what should I underline in the first integral that isn't in the second one yet? The sine of x and also the dx. So that's what we need to build. And lo and behold, it's almost exactly right there. Yeah. So multiply or divide both sides by -1. To get sine x dx is just negative du. Okay, so that's that, and that means that we can come back over here and put a, I'll put the, what can I do here? I'm going to put the du here, I'm going to put a -1 outside, and then I need a placeholder upstairs. There's a 1. So that's our integral. Okay, and again, there are only like 8 things that we can find the antiderivative of. 1 over u du is one of them. That's natural log. So I've got ln. I've got the negative sign carried from the front. I'm going to put u here, but I'm going to ask you guys to start putting something extra is the absolute value. So from now on, oh, we're going to try. On the old smart boards, the 600 series, you could only have 1 pen touch at one time, but I think on the new ones we can do 2. Yeah. Well worth the extra $400. That's awesome. Awesome. Let's see. Yeah, so default now for us every time, you're not going to just put ln, you're going to put ln absolute value. And then finally go back to the x's. U is cosine of x. Let's see. Any questions on that? All right, so now officially everything on that take-home quiz is something that you have seen before. This was the only gap. Let's try number 6. We'll go to Dawn. Okay, so let's try number 6 here. To this day, so I've been doing, let's see, how long ago did I take Calc 2? I took Calc 2 in 1990 something. 1994. I took Calc 2 in 1994. So that's how many years ago? Like 12, how much? 12 and 18. Oh my goodness. Yeah, thank you. Makes me feel good. So back in 1994 is the first time I was exposed to these weird integrals, and now 18 years later, I still suck at them. But maybe you guys will have some more insight that I still don't have. But let's give this a shot. Okay, U substitution, what are we going to let U equal? Stuff in the inside the radical, right? The inside function. U is equal to x minus 1. And I'm hoping we can pause and see if it has potential. And I think some people are shaking their heads because they recognize this doesn't look good, because du is just 1 dx, and there's this x squared, this extra thing that it's not going to work. But let's proceed. So du is equal to 1 dx, just dx. Yeah. And then we'll start to substitute. So the original integral is equal to, yeah, so bare minimum, I want to get my u. So what do I have to write to get the u? Yeah, so I'll write it with the root, and then we're going to change it to a 1/2. So that's the least I need to do to get the u in here. And then we're going to underline what's still missing, x squared and dx. And that's a real problem, because I can't build x squared dx from this without bringing x's into the equation. And x's and u's simply don't mix. Pass it A. That's what we're going to do. The real goal is to get only u's in this thing. And for all the substitutions that we've seen so far, the stuff that's underlined, the missing stuff, you're just going to build, and it'll be du over a number every single time. But we actually have one more tool that we can use to bring u's into this equation. So how about we do this? Forget the x squared, but just look at the dx. What can I put instead of dx? I can put du. Those two things are equal from the last purple equation. Yeah, and then the other piece, I'm going to underline in red, it's x squared. I cannot build that from my last purple equation. Just can't do it. But I can build it from this. So what can you do to that equation to build x squared? First, you're going to add the 1 to both sides, and then you're going to square both sides. So we go u plus 1 is the same as x, add 1. And then trying to build x squared, so we square both sides. So what can we put instead of x squared? U plus 1 squared. I'll underline it in red. That's the x squared. So I'm not saying that integral is any better, but does everybody at least buy that integral is equivalent to the first one? I mean, every piece has been substituted. Okay, so can we deal with this guy? Well, let's go ahead and rewrite that square root. Ernie had pointed out we should put that as a u to the half. And then the u plus 1 squared. Yeah, let's expand it. We're good at dealing with polynomials, so I'm going to FOIL that thing out. Now what can we do? We're going to distribute that thing through, and it'll basically look like a polynomial. It won't be because the powers will be fractions, but we can handle it just using the power rule. So go ahead and distribute that very carefully, and then see if you can do antiderivatives term by term. So did I, uh-oh. The thing was covered. I didn't see the half. So let's, yeah, all right, so we'll fix this one. Thank you. All right, so what does it become? So that's a 2/3 u to the 3/2. Okay, my fault. All right, and then finally, all of those u's become x minus 1s. So I'll be a little bit lazy. Any questions on that one? That's the answer. Mm-mm. Mm-mm. Nope, that's it. It's weird, right? It's not just me. Like, weird is my characterization. This is not like universally known as the weird kind of u substitution. We could start a movement. Yeah, I could just never see, like, for all the u substitutions we did last class, I can look at the integral and I can do most of the u substitution in my head, or at least identify, okay, this is going to work. This has a lot of potential. But for these, no idea. I just try, and then I'm pleasantly surprised at the end if it actually works. Okay, so number 7, as I said last class, u substitution is super important. It's imperative you practice this technique to the point of fluency, not just competency. As I said, over the weekend, I wrote the first test, which is coming up in a couple of weeks. More than half of it involves just straight, find the antiderivative of, and all of those straight ones involve u substitution. Like just about every antiderivative we're going to do this semester is going to involve u substitution because the only antiderivatives we know comprise a very short list. So u substitution allows us to convert things that aren't on the list into things that are. All right, we have a ton of time for this group activity. So let's see if we can get through it. And then if you finish, there's challenge problems, there's homework, there's always more u substitutions to practice. So let's use this time and practice.